Hello everyone, in this work, we present Momentum Incorporated Discrete Neural Network for Multitask Hierarchical Control in an Overdetermined System with Uncertain Physical Parameters. Redundant robots, with their extra degrees of freedom, have the potential for multitask control. In multitask hierarchical control, the key challenges arise. 1. How to control multiple tasks simultaneously. 2. How to learn uncertain physical parameters. To overcome these challenges, a momentum-incorporated discrete neural network for multitask hierarchical control in an overdetermined system with uncertain physical parameters has been proposed. The MIDNN incorporates two subnetworks based on a momentum-incorporated discrete method. A multitask hierarchical control network and a physical parameter learning network. The MHCN enables priority-based multitask hierarchical control in scenarios where the total task dimension exceeds the number of DOFs. Meanwhile, the PPLN is designed to learn uncertain physical parameters, thus improving network adaptivity. The momentum-incorporated discrete method accelerates the convergence of the network. Based on MIDNN, the following for subtasks are defined and applied to the subsequent simulations and physical experiments. It is important to note that the priority of these subtasks is adjusted in accordance with the simulation requirements. The simulations are conducted on the Sawyer robot and physical experiments are performed on the Franca Amica Panda FEP robot platform. Simulation and experimental results show that when the initial learnable physical parameters are uncertain, the MIDNN can rapidly and accurately learn the actual physical parameters of the redundant robot. Based on these precise parameters, the robot achieves accurate multitask hierarchical control. High-priority subtasks of B and C are successfully executed. In contrast, the lowest priority subtask D fails to perform, but its failure does not affect the execution of higher priority tasks. To systematically evaluate the performance of MIDNN, a comparative simulation is conducted by reversing the original task priority order. Specifically, the priorities of the subtasks are assigned as follows: subtask D to B, C, and A as shown in the figures. The three higher priority tasks are successfully executed, while the fourth subtask fails due to an inherent dimensional constraint in the task space. Significantly, the failure of this lower priority task does not affect the execution of the higher priority tasks. To evaluate the impacts of physical parameter accuracy, hierarchical control, and the momentum term on network performance, this section conducts three ablation experiments comparing MIDNN with other networks. Three progressive scenarios are designed as follows. Scenario 1, parameter learning. Scenario 2, hierarchical control. Scenario 3, convergence acceleration. First, the simulations and physical experiments for Scenario 1 are depicted in the figure. To ensure statistical reliability, the network's performance is evaluated over 20 simulation runs, with both extreme and mean values obtained and analyzed. From the simulation and experimental results, it can be seen that since networks 16 and 44 lack the capability for parameter learning, the robot loses control once the physical parameters are uncertain. In contrast, MIDNN enables parameter learning, thereby achieving precise control of the robot. Subsequently, Scenario 2 tested the effectiveness of the MIDNN in multitask hierarchical control. It can be observed that when the total task dimension exceeds the degrees of freedom of the redundant robot, traditional hierarchical control networks cannot achieve simultaneous control of multiple tasks. However, the proposed MIDNN is capable of accomplishing this control. Finally, Scenario 3 demonstrates the effect of convergence acceleration. The results show that while both networks exhibit comparable initial errors, the momentum-incorporated network achieves superior performance with faster convergence speed. These results provide conclusive validation of the significant benefits of the momentum term in discrete systems. These experiments serve to demonstrate the feasibility and effectiveness of our proposed MIDNN. Thank you for your attention.